In this presentation I will talk about the most commonly or frequently used mode parameter estimation methods, which is the curve fitting methods. So we will meet some key concepts, mode parameters, which are not new but will be repeated here. Then we will introduce two new concepts, which are local residual and total residual. And we will use the 2 norm, and we will also introduce least squares errors and a concept we call the approximation error. So, once again, as is known from several of the presentations in this series, the mission of experimental model analysis is to determine a modal system model, and we do this from a set of measured system properties, which are measured frequency response functions. And if we now take a look at a typical example of a measured frequency response function, it may look like this. This is the absolute value, that is the magnitude, versus frequency of a dynamic flexibility curve. And as you can see here, we have some disturbances. It could be noise from the measurement system. And we clearly see here that we have at least 2 resonance peaks. So we may expect to find 2 modes contributing to this frequency response function. And the model we have agreed on to use to represent the modes is like this. So the frequency response function between an excitation point P and a response point K, point means here degree of freedom, can be expressed as sum of contributions from the modes. So this is the contribution from the first mode, this is from the second mode, and so on. So our task now is to find the mode parameters, that is the system poles, S1, S2 and so on, and mode shape vectors represented here with the first mode shape phi1, component k, and so on. And we have to determine these values so that this model here fits our measured data, our measured frequency response functions, as close as possible. That is what we have to do. So, returning then to the measured frequency response function, we introduce, well, if we plot the result, if we simply calculate the model frequency response function, we find something that looks like this if we include 2 modes. And the task then is, of course, to tune or select the mode parameters so that we have as good agreement as possible with the green theoretical model curve and the blue measured curve. And when we have the best possible agreement, then we know the values of the system poles and the mode shapes. So, we have to find the optimum, in some sense, mode parameters of that is the mode shape vector and system poles. So what is then meant with optimum? Well, the most common choice is that we mean in least square sense. So that means that the mode parameters that minimize the least square approximation error is the values, the mode parameter that defines our modal model. So, in order to find out what we mean then with this, we have to introduce an estimation frequency band. This is now, well, the red crosses here denotes or shows our measured data. Actually, the measured absolute value, magnitude of the flexibility, dynamic flexibility versus frequency. So we suspect then that from this peak here, we suspect that we have a resonance peak here, so that we will find a mode in this frequency range. So we focus then by selecting a frequency estimation band like this, in this case between 2.3 and roughly 4.9 Hertz. So this is our estimation frequency band, and we now include these 5 frequency points, frequency lines in our estimation. So we introduce now a local error or residual at a frequency, single frequency fk, as well. If we start from our measure data and then we plot our theoretical model data here, then the local error or residual is the difference, well, supposing then that this is the frequency fk represented by this measurement data, then the difference between this measured value and the model value is defined as the local error or local residual. So with the 2 norm, if we use the 2 norm as a measure, then we actually define the local error, EK, mathematically as the squared absolute value of the difference between the complex valued measured frequency response function and the complex valued theoretical model frequency response function. Next step is to sum the local residuals over the estimation frequency band to get the total approximation error or total residual in the estimation frequency band. So we simply sum all local residuals over the estimation frequency band like this, and then we get capital E, which is the total approximation error, and which is a function then of the system poles and the mode shape vector components. In order to find the best possible mode parameters then, we have to minimize the total residual or the total approximation error. That is, this function has to be minimized with respect to the system poles and the mode shape vectors. And in analysis, mathematical analysis, we learned that to find the stationary points is one step, to find the optimum, minimum and maximum of a function. And in this case, well, in mathematics we solve this by finding the zeros of the partial derivatives with respect to the parameters that we want to optimize the function with respect to. So in this case we must find the zeros to the partial derivative of the total residual with respect to the complex pole, with the system poles, and with respect to the mode shape vector components. So this will then be a system of equations that we have to solve in order to find the stationary points. And the problem now is that this is a non-linear optimization problem. And as we know, this is a very difficult numerical task to find stable, well-defined solution to this kind of optimization problems. And also, I can tell you that there is a quite a large number of implementations of various types of numerical routines that does this job for you. We will, in a later presentation, present the complex exponentials method, which is one very, very useful type of routine that estimates the mode parameters for you. But that will be in a later presentation.